Continuing our short video lecture, we've been talking about drought in California and the challenge with water supply to the people that need it for drinking water, as well as water supply to the farms for irrigation, as well as additional uses for the water in that region, which brings up the topic of water supply treatment. Water treatment is done to reduce health risks and improve the aesthetic qualities of water. Sources of water supply could be surface water resources such as rivers and lakes, or groundwater resources in aquifers deep beneath the subsurface. So the source could be groundwater, a river, or a reservoir or a lake. The treatment needs of a water system differ depending upon where the water comes from. Groundwater typically requires less treatment than surface water resources. Common surface water contaminants include turbidity or sediment, microbiological contaminants, and low levels of a large number of organic chemicals. Groundwater contaminants include naturally occurring inorganic contaminants such as arsenic, fluoride, radon, and maybe some organic chemicals from a pollutant source. If the groundwater source is shallow versus deep, then bacteria and viruses could be potentially found in the shallow groundwater. So the water has to be treated in order to make sure that it's safe to drink, as well as it has good aesthetic qualities in terms of it looks good, smells good, and tastes good. The treatment technologies fall into three categories. Physical treatment, which doesn't produce a new substance. It typically involves evaporation or filtration, some type of screening of the material, or aeration. So physical treatment doesn't produce a new substance. Chemical treatment forms a new substance through processes like coagulation, disinfection, water softening, or oxidation. And then biological treatment uses living organisms to bring about chemical changes. So there are multiple types of treatment processes listed on the screen in front of you, and then these are pictures of a treatment water supply treatment plant. So since we're talking about water supplies being provided to public communities, it's important to bring mention of what happened in Flint, Michigan. So Flint is a city located northwest of Detroit in Michigan that was once home to a growing auto industry. It included the headquarters of General Motors. After General Motors relocated, the city deindustrialized, and it began to go through urban decay, losing population and income. The Flint water crisis occurred in April 2014, and what happened was that the city tried to save money, so they switched from the Detroit water supply, which sources its water from Lake Huron and the Detroit River, to a different source called the Flint River. So this was done in order to cut costs when the city was under a state-appointed emergency manager. The city started draining the water from the Flint River, treating it locally, and saving millions of dollars. All the decisions made at this time were at the state level, which the state officials confirmed, but not by the city council or the mayor. So what happened was that the Flint River had different water chemistry than the previous water supply. It contained chloride ions from salt runoff, and when the water contains such chemicals, it must be treated with anti-corrosives. The city failed to treat the water supply with the anti-corrosive materials. By summertime in 2014, residents started to complain about the water quality in their homes to the state. The state told them to boil their water and it would be safe to drink. The state actually did not formally step in until about a year later to take any action. Residents continued to notice different colors of water and that there was an odor coming from the faucets. The water also tasted funny. Some stated that they had rashes and clumps of hair falling out. According to Virginia Tech, the Flint River is 19 times more corrosive than Lake Huron because it differs in water quality chemistry. So the State Department of the Environmental Quality wasn't treating the Flint River water with an anti-corrosive agent, and this results in it being in violation of the federal law. Therefore, the water was eroding the iron in the water mains, turning the water brown, as is depicted in the picture in the bottom left corner. About half the service lines in Flint homes are made out of lead, and because the water wasn't treated properly, lead started leaching into the water supply, also with the iron from the pipes that it was actually flowing through. This was going on for about 2 years. In addition, there were children that were drinking the contaminated water that had lead in it, and the result was that children were showing signs of lead poisoning. Behavioral learning problems, lower IQ, slowed growth, anemia, and even seizures. In adults, too much lead in the blood can lead to kidney problems and reproductive failure. If a pregnant woman were to ingest too much lead-contaminated water, it could potentially lead to premature birth and birth defects for her child. So, what ended up happening was the water in Flint, the source water was switched from Lake Huron and Detroit River to that of the Flint River, and the end result is just the variation in that water chemistry between those different sources. It led to the corrosion of the pipes within the water distribution system in Flint, as well as the water distribution system within the homes of the residents of Flint, and lead was leached out from the pipes into the water and people were drinking it. The diagram on the right shows the percentage of children 5 years old and younger that tested with elevated blood levels greater than the allowable level according to state data. So it appears that the water service was switched from Detroit Water to Flint River in April 2014, and there was a spike in the lead levels that were documented. And then a local pediatrician measured blood levels for children ages 5 and younger in Flint before and after the switch, and her findings are depicted here. That all of Flint and areas with high lead in their water levels in Flint prior to the switch had about 2.5 to 2.1% lead in their blood, and then after the switch there's a definitive increase of 4 to 6.3%. There were times at which the lead levels in people's homes exceeded the safe drinking water standard, and this went on for quite some time until the community was able to get the local government as well as the state government to take it seriously and to address the problem at hand. So this begs the question, if we rely on water supply companies to provide us with water, and there's a potential risk that the water could be contaminated, despite the fact that they have to meet safe drinking water standards, should we instead use bottled water? Is bottled water the answer? So, tap water is on average 500 times cheaper than bottled water. So bottled water can be quite expensive. It's almost like pouring money down the drain. Bottled water costs between 89 cents per gallon to about $8.26 per gallon. And compare that to a fractions of a penny for water that comes from your tap. So bottled water can cost more than 1,000 times greater than that of tap water. Also, bottled water is not necessarily safer than tap water. In fact, more than half of the bottled water that you purchase from the shelf of the grocery store actually comes directly from a water treatment plant. So the diagram here is showing plastic recycling going on at a recycling facility, and then the data table here shows the consumption of bottled water in the top 10 countries between 2000 and 2005, and it looks like the US has the largest consumption of bottled water compared to any other country in both years, both in 2000 and 2005. So when we use water and we're done with the water, like doing our laundry or taking a shower or going to the bathroom, that water needs to go somewhere. The gray water component is the water that is from the washing machine or the laundry or doing the dishes. And that could actually be recycled on site at a home and be used to water the flower beds or something to that extent. But the non-gray water, the water that's coming from the toilet, has to go somewhere appropriate to be treated. Now, if you live in a rural community, it's likely that you have some form of a private conventional septic system or sand mound system on your property that takes care of the toilet water. And usually it goes into what's called a tank, and then it goes into a leach field where it allows bacteria to naturally break it down. If you live in a city, however, when you flush the toilet, that goes into a pipe collection system, which then pipes all that sewer water to the local wastewater treatment plant. Wastewater treatment plants are also known as publicly owned water treatment works, or POTWs. They use a combination of physical, biological, and chemical treatment methods to make the water safe in order to be discharged into a stream. Now here's the deal. The goal of wastewater treatment is to reduce the biological oxygen demand, the amount of suspended solids, the nitrogen, the phosphorus, and the ammonia. Let me be very clear that the goal does not include toxic chemicals or pharmaceuticals. Industry discharge can contain lead from manufacturing of batteries or cyanide from electroplating shops. Wastewater treatment plants are not equipped to treat these pollutant industrial waste, and hence these can interfere with the wastewater treatment process at a publicly owned treatment work. So the primary purpose of pretreatment at an industrial facility is to remove those pollutants which otherwise would just go right through the publicly owned wastewater treatment plant, because the POTWs, or the publicly owned wastewater treatment plants, are not equipped to remove special pollutants. So the pre-treated water plus whatever water is coming from residential toilets go into a collection system and make its way to a wastewater treatment plant, and it goes through 2 and maybe 3 steps of treatment. The first is primary treatment, and that's where the wastewater is sent through physical processes that screen the wastewater and remove any kind of rags or grit or debris and sediment. So anything that floats or settles that's not in water phase is removed during the primary treatment phase. The secondary phase is where the treatment technology focuses on small microorganisms which actually feed on and digest and reduce the amount of organic matter in the wastewater. This can be done with trickling filters, which is what's depicted here in this picture. Also, there's activated sludge, which is depicted here in these containment locations. There's aeration lagoons, which is depicted here in this picture, as well as rotating biological contactors, or RBCs. A third level of treatment includes the tertiary treatment, and this is where advanced treatment is done to remove nitrogen and phosphorus nutrients and most of the biological oxygen demand, or biochemical oxygen demand. So this is a diagram depicting primary and secondary sewage treatment. The first 3 steps in primary treatment involve the physical separation of grit and materials that can settle to the bottom of the tank and be removed as sludge, or float on the surface of the tank and be removed with a skimmer, or just be removed as grit. So sludge is a byproduct of wastewater treatment, and historically we used to dispose of it in a landfill, but now we can actually do additional sludge treatment processes which allow us to utilize it for farm field application because there's a lot of nutrients in this sludge. This portion of the diagram depicts the secondary treatment that occurs at a wastewater treatment plant, and the focus is on removing any additional solids from the system, as well as any biochemical oxygen demand, and killing bacteria and removing nutrients. One thing worth noting is that pharmaceuticals and personal care products are not removed through wastewater treatment processes, and as a result, these are now considered emerging contaminants of concern. And I'll talk more about these in the next lecture.